we go. There we go. Boop. I believe in you, laptop. Okay. So we were talking about covalent bonds, right? That's kind of where we left off. I just can't get all of the things in order at once. So we're talking about covalent bonds, right? And ionic bonds. We had ionic bonds where you had atoms with charges and they were giving electrons, right? Like a sodium would give an electron to a chlorine. So you end up with this kind of crystal form. Gotcha, Grant. Okay. And then we talked about covalent bonds, right? Which was this nitrogen situation where we're not handing electrons from one atom to another. We're sharing pairs of electrons between atoms, right? So there's no charge, right? No net charge. We've still got a full outer energy level. Every little electron has a little buddy. Everything is stable. Everything is happy, right? Those were our covalent bonds. There we go. Now, except, right? It can never be that simple. So in covalent bonds, we have to deal with something called electronegativity, right? And electronegativity is just an element's affinity for electrons, right? And it increases, if you remember the periodic table we were looking at last week, it increases from left to right on the periodic table. So on the right side of the periodic table, those elements are more electronegative, have a higher affinity for electrons. So when they are sharing electrons, if they have more electronegativity, they're going to hold the electrons a little bit closer, right? They're a little bit greedy. They're going to hold the electrons a little tighter versus things on the left side of the periodic table, which will kind of hold on to them a little more loosely, right? Let them kind of get a little bit further away, right? So things on the right side of the periodic table are more electronegative, and also at the top, right? So electronegativity decreases from top to bottom and decreases from right to left. So the top right corner has your most electronegative elements. Bottom left would be the least electronegative. All right. So knowing that when molecules are forming and they're forming these covalent bonds, that there might be differences in electronegativity, it gives us the ability to kind of add in a bit more vocab to kind of describe them a little more specifically. So if we have a molecule where the electronegativity of the atoms is equal, right? Easy to see in things like hydrogen and oxygen gas, right? Because we have a hydrogen bonded to hydrogen. They're the same element, so they definitely have the same electronegativity. They are definitely sharing their electrons equally, right in the center between the two atoms, right? So electronegativity is equal. The electrons are equally shared, and so we call those bonds non-polar covalent bonds. All right? We're talking about covalent bonds where electronegativity is equal. They are non-polar. Conversely, we could have atoms bonding that differ in their electronegativity, in their affinity for electrons, right? In which case the electrons aren't shared equally, right? For example, oxygen is always our super electronegative biological element, right? Of all the things we talked about, oxygen is way right, way up, right? So if we're talking about water, which is oxygen here, hydrogen way over on the left, right? They have very different electronegativities. Oxygen is more electronegative. It is going to hold electrons tighter to itself versus hydrogen, which is much less electronegative and is going to kind of let those electrons be a little further away. Okay. Now, if you have atoms with differing electronegativities, the electrons are shared unequally, right? In the case of water, they're closer to the oxygen. You get a partial charge. It's not a full charge. Hydrogen hasn't given it its electron away, but it's kind of letting it, right? It's got like a longer leash, right? It's a little further away, a little closer to the oxygen. And so we call them polar. Right? If you think about poles as being kind of the opposite ends of things, right? Now we kind of have a more negative-ish pole and a more positive pole, right? We've kind of made it a little uneven, right? And this is a big characteristic when we're talking about water, which has a big effect on living stuff, right? So at the end of this chapter, we're going to circle back and spend a good chunk of time with water, right? But suffice to know now, when we have atoms where electronegativity is equal, electrons are equally shared and they're nonpolar. If you have an atom and a molecule that's kind of holding the electrons a little bit closer, that molecule becomes polar. Okay. Now, we've made molecules. We can kind of describe molecules and the bonds that they're making. And so when we start mixing compounds, right, we're going to start making and breaking these bonds, these covalent and ionic bonds. Right? And the formation and breaking of chemical bonds is called a chemical reaction. Easy enough, right? And so this is just the shifting of atoms from one molecule to another. Right? If you happen to, honestly, my high school chemistry class was pretty subpar. I didn't get much, but depending on your high school chemistry class, maybe you spent some time balancing reactions, right? This is the general reaction for photosynthesis, right? Water and carbon dioxide yield sugar and oxygen, basically, right? And so there's no change in the number of kinds of atoms, right? We're not creating and destroying particles, right? We've got 6 carbon right here. We still have 6 carbon here. We've got 6 times 2, 12 hydrogen here. We still end up with 12 hydrogen on the other side. We're just moving them around. We're changing the way they're attached to each other, right? And so we generally write this as reactants and products, even though most chemical reactions are kind of bouncing back and forth, but we tend to write it in a direction, right? Photosynthesis, we're taking water and carbon dioxide and making sugar and oxygen, right? Right. Now, reactions happen at some speed, sure, right? They're happening, they take some amount of time, but we can kind of change the amount of time a reaction will take, right? If we change the environment that the reaction's happening in, right? So we can make reactions happen faster by doing a couple things, right? You can heat them up, right? If you're trying to, it's a pretty lame chemical reaction, but dissolve like sugar and water. If you heat it up, the sugar dissolves faster, right? Because the particles are moving faster, the reaction happens faster. So you can heat things up, or you can increase the concentration of reactants and products. And this one's a little harder, I feel like, to kind of grasp, but it makes sense if you think about the fact that like these atoms and these molecules, they're not interacting with intention, right? It's not like hydrogen's going to go find some oxygen because it wants to make water. It's just that atoms and molecules and compounds are bumping into each other, right? And their electrons are interacting however it is that they will naturally interact, right? So if you have some system where a reaction is taking place and you just increase the amount or the number of those molecules and compounds, they're going to bump into each other and react more often because there's more of them there to interact, right? So we can increase chemical reaction rate by increasing temperature or increasing the concentration of the reactants and products, right? We can also, and we'll basically kind of spend a good chunk of an entire unit on this, incorporate things like catalysts, right? A catalyst is some substance that facilitates a reaction, that speeds up a reaction, things like enzymes, right? When we get into photosynthesis and respiration, we'll be talking a lot about enzymes, and enzymes are molecules that function to increase chemical reactions or make chemical reactions more efficient, right? So this gets us to, right, we've talked about elements, compounds, molecules, reactions. We keep mentioning water. So let's just talk about water, right? Basically, life on Earth is possible because there is so much water, right? If you are kind of into those like alien worlds, sort of shows, right, the way they kind of look for potential planets, right? They're looking for water, right? Because water just facilitates a whole lot of these reactions and interactions that we're going to be talking about. So we're going to talk about kind of the structure of water, how that causes water to be kind of a weird substance. We think of water as being pretty boring, right? It's just water, but it's actually kind of a weird compound when you really start looking at the way it behaves. And those properties kind of basically make life possible at kind of the broadest level. So hydrogen bonds, right? If you're paying close attention, you'll notice I mentioned 3 kinds of bonds, and then we only talked about 2, right? We covered ionic and covalent. That third kind of chemical bond was a hydrogen bond. And they're these really weak bonds that happen between the hydrogens on molecules. So here's how it happens. So we've got a couple hydrogen here. We've got 1 oxygen. They're probably going to be friends, right? We've got hydrogen with a couple unpaired electrons. They don't like that. Oxygen has 2 unpaired electrons. It doesn't like that. So we can pretty easily form 2 single covalent bonds, right? Hydrogen is sharing its electron with oxygen here and here. Right, so we form 2 single covalent bonds. We've got a water molecule. Now, like we mentioned, oxygen is really electronegative. Hydrogen, not so much. So when oxygen is sharing electrons with hydrogen, it is actually pulling those electrons closer to itself. Hydrogen kind of has the opposite issue. It's not holding them so tight at all. So it kind of compounds the issue of the electrons spending more time on this side of the molecule, right? And so what you end up with is a polar covalent bond. The electronegativity is not even, right, across the molecule. Subsequently, we then call this a polar molecule, where since the electrons are spending more time over here, this side of the molecule is slightly negative. Because the electrons are spending less time over here, this side of the molecule is slightly positive, okay? So there's no full charge, right? Hydrogen hasn't completely given its electron away, but it's kind of letting it roam a little further, right? So you get these partial charges on water molecules, right? And this allows for hydrogen bonds, right? So if we have water molecules that are a little negative on one side and a little positive on one side, right, you're going to get these hydrogen bonds. Their slightly positive charge is going to get attracted to the slightly negative charge of the oxygen, right? They're really weak. It's just, we call it an association. It's not a bond. But these hydrogens are going to kind of be drawn to the negativer side, the more negative side of this oxygen, right? And just weakly, right? So you end up with these water molecules kind of being drawn together. They kind of stay associated between these partial positive and partial negative charges, right? Because positive and negatives just naturally attract. And this becomes really important in the structure of these large biological molecules that we'll be talking about in chapter 3, right? DNA and proteins, carbohydrates, other things, right? Because these kind of hydroxides and water molecules basically cause things to be sticky. That's where we're headed. You can kind of think of water as being a bit sticky, right? So we've got a couple words for the stickiness of water. Water is both cohesive and adhesive, right? Cohesive was what we were just talking about, right? Because water is carrying these partial charges, water molecules are attracted to other water molecules, right? The negative side of this one is going to kind of be a bit stuck to the positive side of this one, right? So water is cohesive. Water molecules stick to each other. This is what causes surface tension. If you have a container of water, the molecules on the top that kind of form the surface of the water are sticking to, being drawn down towards the molecules below them. And you get this kind of, not quite a film, right? But that surface tension, that kind of sticky top to water, if that makes sense, right? Right? Because the H2O molecules on the surface are attracted to the molecules below them, right? So water molecules are attracted to other water molecules. But water is also adhesive, right? So they will kind of add themselves to other things, right? So we've got cohesive, they stick together, adhesive. Water also is attracted to other polar molecules, right? Because water is not the only polar molecule. There's other molecules that have these kind of partial charges. And so water, having these kind of partial negative and partial positive charges, is also going to be attracted to other molecules that are also carrying these partial charges. It's going to work just the same way, right? So water is cohesive, it sticks to itself, and it is also adhesive. It sticks to polar molecules. This is what causes capillary action. If you put like glass, like a glass tube in water, you see the water kind of rise up the tube. It's because the water is sticking to the molecules on the inside of that tube, right? You're going to spend, I think in 2 weeks, basically a whole lab playing with water, right? Looking at the different properties of water. So water is cohesive and adhesive, right? Now, because water is cohesive and adhesive, right, because it has these characteristics, right, because it forms these hydrogen bonds with itself and with other things, we have a lot of kind of interesting properties of water that will change or affect how water behaves in living stuff, right? So we're spending a little time there, right? Enter next numbered list, right? So properties of water, I think there's like 6 we're going to talk about. So the first one is that water has a high specific heat. Specific heat has a specific definition, right? So specific heat, specifically, is the amount of heat needed to increase 1 gram of substance 1 degree Celsius, right? So how much, if I have a gram of water, how much heat do I have to put into it before it increases in temperature 1 degree Celsius? Okay. Oh, no, so no, you don't have to know. You don't have to know. No, just that. So specific heat is how much heat is needed to increase a gram of something 1 degree Celsius. And water, we don't have to know specifically how much, just that it's a lot. It takes, relatively speaking, a lot of heat energy to increase the temperature of a gram of water 1 degree Celsius, right? And if you've ever sat and wait for water to boil, right, you know, it takes a while, right? Water heats slowly and then holds that heat for a fairly long time, relatively long time, right? So water has a high specific heat. It takes a lot of energy to heat it up, and once it's warm, it stays warm. This allows for a couple of things to happen in living systems, right? It means we can maintain a fairly constant internal temperature. We're mostly water. So if our body gets itself to a certain temperature, the water in our body will kind of just hold that temperature. It's almost got kind of like an insulation kind of property to it, right? Makes it easier for us to maintain a constant internal temperature. Water also can absorb a lot of heat, right, without getting hotter. And this is that weird thing where we're talking heat versus temperature, right? Heat as energy versus like temperature Celsius. So when I say heat, I mean energy, right? Because heat is energy. So your cells, right, all your cells, they're doing metabolism, respiration, all these things are happening all the time. And all of those chemical reactions are releasing energy in the form of heat. Now, it would be bad if all of these metabolic chemical reactions in your body were just constantly heating your body up to the point that you just overheated. But because we're full of water, it can absorb a lot of that energy and again, help us to maintain our constant internal, nice, happy temperature where all of the reactions are happening at the rate that they're supposed to, in the way that they're supposed to. So property 1 of water, it has a high specific heat. It heats slowly and it holds heat for a long time. Okay, high specific heat. Kind of as a result, related to this, the second property of water is that it has a high heat of vaporization. So heat of vaporization is the amount of energy needed to change a gram of substance from liquid to gas. Right? And it tracks, right? If it takes a lot of heat to increase the temperature of water, it's going to take a lot of energy to turn water from liquid to gas, right? To raise the temperature such that it evaporates or vaporizes, right? So water has a high heat of vaporization. And so because a lot of energy is kind of used in evaporation, it cools the surface where it happens, which means we can hold water inside of us. We have water inside of us that kind of keeps a constant temperature, right? Absorbs a lot of energy. But if we secrete that water onto the surface of our body and allow it to evaporate, we can kind of, right, control our temperature the other way. We can cool our bodies that way, right? By allowing the water to be secreted to the outside and evaporate. And it kind of takes that heat energy away from us by evaporating, right? So water has a high specific heat, heats slowly and holds heat. Also has a high heat of vaporization. It takes a lot of energy to turn water from a liquid to a gas. Okay. 3. This is kind of a weird one. It just seems kind of like odd. Solid water is less dense than liquid water. Solid water, of course, being ice, right? Ice is less dense than liquid water. We know this. Ice floats in water. Why would that matter? We're not full of ice, ideally. But what it means is that kind of the ecological implication is that like out kind of in the environment, ponds, rivers, streams, lakes, where things freeze, those bodies of water will freeze from the top down. Because they freeze from the top down, frequently, there is some portion of that body of water down towards the substrate that does not freeze completely, right? And because of that, aquatic organisms, fish, frogs, other things, can survive the winter, right? If it froze from the bottom up, those things would be kind of pushed up and out of the water, which would be problematic. And they would be really cold because they would be exposed to the environment. Instead, water freezes from the top down, and you kind of end up with this insulated situation at the bottom where these aquatic organisms actually can survive these kind of frozen periods of time, right? And general theories being that most life started in aquatic habitats, right? This becomes a very critical component kind of the biosphere, right? And how it behaves at the broadest scale. So solid water, right? Ice floats. Property 3, ice floats. Number 4, we kind of mentioned this when we're talking about ionic bonds. Water is a solvent. Okay? So polar molecules and ions dissolve in water. We know this, right? Our ionic bond example was table salt. If you put salt in water, it dissolves, right? Dissociates into the water, right? And so you basically have kind of these free ions floating about in these aqueous systems, like the inside of your body, right? And so these ions are important in biological systems. We'll be talking about things like calcium, especially if you're going on to anatomy and phys, you're going to be hearing about ions till you can't think ions anymore. Calcium, potassium, sodium, right, are important in a lot of things, right? Calcium in cell signaling, potassium and sodium in conducting nerve impulses between neurons and things, right? The fact that these ions kind of stay free in aquatic or liquid environments, right, means that they can be used in cell membrane channels, which is something we'll cover later in the semester, right, and lots of other kind of physiological processes. So water is a solvent. It's also why Kool-Aid works. All right, 5. 5 is kind of a strange one, or it sounds kind of weird. Water organizes nonpolar molecules. What the heck could that even possibly mean? Right, it's just water. But water is greedy, right? So water is polar, sticks to itself, sticks to other polar stuff, and like it wants to form hydrogen bonds with every single thing it could ever possibly find to hold like a hydrogen bond with, right? Which is mostly water sticking to water, but also water sticking to other polar stuff. Now, this affects the way it interacts with other things, right? So if water comes into contact with a non-polar substance, there are no hydrogen bonds to form. Non-polar substances don't form hydrogen bonds. Now, water is really interested in forming hydrogen bonds, and it is very opposed, I'm like anthropomorphizing the heck out of water right now, to interacting with things that cannot form a hydrogen bond, right? So a non-polar substance like oil right? Water will kind of actively push it away, right? And so that's where these substances get called hydrophobic, because they'll be pushed away, they'll be excluded from the water, right? Kind of the root of hydrophobic is water fearing. So if something is nonpolar, if it doesn't carry any charge or even a partial charge, the water is going to just push it away because it's looking for hydrogen bonds, right? It's being attracted to other hydrogen bond or polar things. Polar molecules readily form hydrogen bonds. Water is all about it and will stick to that stuff wherever it finds it, right? And so those substances, other polar molecules, are called hydrophilic or water loving, right? So you put polar stuff in water, the water is going to just like grab it, right? And it's going to exclude anything that it cannot form a hydrogen bond with. And that exclusion is then called hydrophobic exclusion, right? And this is how water organizes nonpolar molecules, right? Because of the way that these molecules are going to push nonpolar things away, it's going to exclude these hydrophobic molecules. Those hydrophobic molecules will then end up aggregated, right? They're going to be pushed away from the water. They tend to take specific shapes, right? If you pour oil in water, they tend to make these very kind of spherical little globs. It's because the water's pushing it away, and subsequently they're kind of all joining together, right? So that's hydrophobic exclusion. And this affects lots of stuff. So chapter 3, we're talking about biological molecules, and all of these molecules have different like polar and non-polar regions, and we're full of water. And so it's going to affect the way that these molecules interact with each other, with water, and all kinds of things. This is how biological membranes, your cell membrane, forms because of hydrophobic exclusion, right? So we'll get there in chapter 3. Now, last water property. Water forms ions. So if you've got water, some amount of those water molecules are going to dissociate for whatever reason, right? They're going to come apart, right? So we've got H2O. When they dissociate, if a water molecule dissociates, it breaks into a negatively charged hydroxide ion and a positively charged hydrogen ion, which is just a proton. If you pull the electron off of hydrogen, you've just got a proton, right? So in water, there's some amount of dissociated water molecules. So you've got these little positively and negatively charged ions bopping around in your water. All right. Which gets us to acids and bases. Right? Because as we will find, the kind of relative proportion of those hydroxide and hydrogen ions are how we determine whether something is an acid or a base. So let's do that. All right. Things can be acids or bases. We talk about the acidity or basicity of a substance, right? And so the acidity or basicity of a substance is determined by the concentration of those hydrogen ions, right? Protons. The concentration of protons and hydroxide ions in whatever substance, liquid, that we're talking about. Now, pure water, where some of our hydrogen and hydroxide has dissociated, has a proton concentration, right, a hydrogen ion concentration, right? That's what these, right? These square brackets just mean concentration, of 10 to the -7 moles per liter. And we can say, and water is neutral, right? Water, just regular old pure water, is neither acidic or basic, which kind of makes sense, right? If we're looking at kind of a balance of hydroxide and hydrogen, and each water molecule that dissociates makes one of each, we're going to have a balance of positive hydrogen ions and negative hydroxide ions, because that's all that's there. All right. But not everything is pure water, obviously. So we have the pH scale, which is kind of how we measure how acidic or basic something is, right? And so pH just means the power of hydrogen. Sure. All right. And pH is equal to the negative log of the concentration of the protons. Don't worry, we're not going to do math. I'm just showing you what it is. pH is equal to the negative log of your concentration of protons. All this means, and it'll make sense when we kind of look at an example, all this means is that the pH is equal to the exponent of the concentration times -1, which sounds even crazier, but the pH is equal to the exponent of the concentration times -1. So neutral water, we said had a pH or had a proton concentration of 10 to the -7 moles per liter. Cool, fine. Right? -7 is our exponent. -7 times -1 is 7. So neutral water has a pH of 7. Yeah? So if I say that something has a pH of 7, it just means that it's 10 to the -7 moles per liter proton concentration. Same thing for, right, if it was 8, something has a pH of 8, the proton concentration in that liquid is 10 to the -8 moles per liter. All right. That's how pH works. I'm never going to have you calculate pH. Right? But neutral water has a pH of 7 because of the concentration of protons. That's how they get that. All right? The scale, right, 7 being neutral, runs from a pH of 1, most acidic, to 14, most basic. And each number indicates a 10-fold change in acidity. Right? So an acid with a pH of 4 is 10 times more acidic than an acid with a pH of 5. And 100 times more acidic than something with a pH of 6. Okay. Right, so we've kind of got this scale right from the most basic to most acidic things, kind of common stuff that we see around, right? Lower numbers more acidic, larger numbers more basic acids. Now kind of up here on the top, right? Any substance which dissolves in water and increases the proton concentration. Right? So liquids that have a high proton concentration have a low pH. Right? Because we're in 10 to the negative, right? And so the larger your negative exponent is, the smaller the number is. Does that make sense? Right? So it's a little counterintuitive, but like a smaller number, this means like 0.1, 0.001, 0.0001, right? So acids have a higher proton concentration, and so the pH number, because it's the inverse, we multiply it by -1, it has a lower pH. They tend to be sour, right? Lemon juice, wine, actually rain is slightly acidic or very acidic if things aren't going well. Bases, right, are just going to be the opposites. Any substance which dissolves in water and decreases the concentration of protons or increases the concentration of hydroxide, right? So you're going to have a low proton concentration, right? 0.0000001 concentration of protons, right? So you have a higher pH. They tend to be bitter. They tend to be soapy. Detergents, bleaches, baking soda, right, are basic substances. Right. Now, we have acids, we have bases. Subsequently, in living systems, because we don't want anything to get too acidic or too basic, we have buffers. A buffer is something that can resist change in pH. So a buffer, right, in the presence of an acid, which has a lot of hydrogen ions, will release hydroxide ions, right, and balance the relative concentrations. Conversely, a buffer in a base where there's a lot of hydroxide ions will release hydrogen ions, right? So a buffer is just going to like make acidic things more basic or bring them back to neutral. And again, bring bases back to neutral. In living systems, we frequently see a pair of substances, right? Because most life, right? Most life exists between 6.5 and 8.2. Our internal systems tend to stay pretty neutral. And our bodies want to stay pretty neutral. So we have things in our bodies which kind of keep acidic or too basic. right? They tend to occur in pairs, carbonic acid and bicarbonate pairs that stabilize the pH, for example, in your blood, right? Acidosis in your blood is real bad. You don't want that. So there are things in your blood already that if your blood starts to become too acidic, bring it back down to neutral or up. pH is going up, but right, bring it back to neutral. Right, so buffers help bring acids and bases closer to a neutral pH.
Is that what acid reflux is?
So acid reflux is a bit more complicated. I think technically acid reflux is actually, I think, closer to a lack of stomach acid because your body kind of overflows your stomach. Things get backed up because you're not making enough acid to digest your food. But it causes the acid to get pushed up into your throat, which is why you take things like Gaviscon and milk of magnesia and basic things because it feels good. It kind of pushes the acidic feeling back down your throat. And this is more of an anatomy and phys thing, but yeah, the pH in your stomach is actually super, super low. It's very acidic. I can't remember exactly what the pH in your stomach is. I want to say like in the 2-4 kind of situation. But right, the tissue, your stomach is lined such that, right, that acid theoretically shouldn't get anywhere else. If it comes up into your throat, that's painful and it causes irritation and all kinds of other things, right, which is what reflux is. But your stomach has other things going on to kind of keep the acid where it needs to be, right? Because you don't want that getting out into other parts of your body that need to stay neutral. All right. So that's got us at time. So when we come in on Friday, we'll kind of have a little brief review of chapter 2, move on into chapter 3, which is the last section for this unit. All right, which will be biological molecules.